Thank you so much for coming. Can everybody hear me okay? Okay, great. Awesome. So my name is Harry. I focus on inference serving at NVIDIA. And today I would like to talk to you about Dynamo, which is a new inference serving stack that we created this year. So last year, when we presented here at the Ray Summit, we talked about our marquee inference serving solution at the time. It was called Triton. And we talked about how RayServe is really well integrated with Triton. So in this case, RayServe is going to facilitate the load balancing and scaling. And then Triton offered our multi-backend, which is, you can use it for deploying onto, say, PyTorch or TensorFlow, Onyx, and all these things. But over the last year, we noticed that there is a shift in paradigm where, most notably, if you think about DeepSeek R1, it's a really incredible model, but it actually pressures on things like compute and memory, and then also there are a lot of challenges that you have to circumvent for scaling and routing. And so we really thought that we have to come up with something new, and we decided to take a more systematic approach for inference serving. And that's why we thought that the old way of doing inference serving with Triton was not really suitable. And so we created a Dynamo. And if you attended Jensen's keynote at GTC this year, he talked about Dynamo as an AI operating system. And it's really true, because we spent a lot of effort making really solid foundation for scheduling, memory management, data transfer. And I am going to talk about this disaggregating serving that you see in the center of the three circles in a little bit. But this is a key use case that Dynamo tackles. And in order to enable this disaggregating serving, which separates prefill and decode from LLM and try to assign it to different GPUs, in order to actually do this disaggregating serving, you need to be able to schedule prefill and decode onto different GPUs so that you can avoid interference. But also at the same time, you want to be able to extend the memory management so that you can utilize the entire hierarchy of the memory and also storage that's available to you in data center. And then the third part is the data transfer. And so you need to be able to efficiently pass the KV cache between multiple nodes. And so that's why we spent a lot of time and effort making the foundation very strong. And so the idea is that even if you have a new technique that's not disaggregating serving, you'd be able to readily support that. And so I talked about how we thought about this from the systems perspective. And so that's why we offer system-level optimization. And I'm going to give you some examples later. But some of the system-level optimization that we provide comes from things like highly performant tokenizer or smart router, or being able to manage the KV cache across the multiple tiers, which is facilitated by the KV block manager. But these system-level optimization can be augmented on top of the inference engines. And so we are really big supporters of the ecosystem. So as you can see, Dynamo actually supports all the inference engines, so vLLM, SGLang, and TensorRT-LLM. We don't just support our own engine. So that's something that I wanted to highlight here. One other thing that we really focused on with Dynamo is that we wanted to give you a modular solution. So we understand that not everybody wants to take the entire thing. And so while Dynamo is well integrated with each of the components, you can actually take any of these components and then run it standalone. And so if you attended keynote this morning, I think there was a portion where they talked about being able to transfer the weights using Nixel between inference and training. And this is how the approach that we took with modularity is really kind of helping the developer ecosystem. And there are many other tools and features that I'm going to talk about that are created in a modular fashion. And so we hope that the developer can really leverage these things. Last thing is about production-grade serving. And so, yes, you can get all the performance optimization, whether it's at the system level or with the engines. But it's really important that we provide a production-grade serving so that you can enable going from configuration to production easily. So I will focus on the system-level optimization and then also production-grade serving. Those are the two main topics. But before I get to that, I just wanted to talk about disaggregating serving a little bit here. And so disaggregated serving is a really powerful technique because, and I'm pretty sure everybody has heard about disaggregated serving at this point, but within the LLM, there's mainly two phases, and so prefill and decode. Prefill is like if you're talking to someone, and if that person is processing the context, that's the prefill phase, and then if the person starts talking after processing all the context, that's the decode. And as you can see, they are quite different in terms of their compute characteristics. So prefill is compute bound, and also decode is memory bound. So the idea is that if you actually separate these two phases, and if you assign them to different GPUs, then you can actually unlock even better performance because you can actually scale them independently. And so it gives you many more opportunities to play with the combinations of different parallelism for prefill and decode. And that's why it gets the performance of this, or the disaggregating serving actually unlocks performance as you scale out. So on the next slide, I'll kind of show you the example here. So this result is a little bit dated. We actually did this at GTC, but I just wanted to highlight some key points here. So this is applying disaggregated serving to Llama 70B. And what you're seeing here is two plots. The left plot is for doing disaggregated serving with a single node. So in this case, using 8 H100s. And then on the second plot, you see the result for 2 nodes, so 16 GPUs. The way to interpret this chart is that it's a bit hard to see, but on the y-axis, it's basically saying it's throughput per GPU. And then the x-axis, it denotes inverse of latency. And so it's tokens per second per user. And if you look at both throughput and latency on the same scale, then obviously you're going to be able to see the trade-off between the two. And the dots that you see here are the combinations of the different parallelism that we've applied. And so the parallel curve is drawn out for both aggregated serving and disaggregated serving. And if you look at the single node result, you can see that about 30% uplift comes from applying disaggregated serving. But if you look at the 2-node result, you'll be able to see that there are more than 2x uplift in terms of throughput per GPU. And so we notice that this is actually a pattern because as you scale out, you have a lot more opportunities to play with different combinations of parallelism for prefill and decode. And that's why it unlocks incredible performance as you scale. So I think in the training case, you are lucky if you're linearly scaling, but since this is measured for throughput per GPU, you're actually breaking this linear scaling law, and that's why this is a hero use case. And if you're using, say, MOE, you can actually apply even more optimization techniques to unlock more performance. And so a technique is called YDP, or sometimes referred as a large-scale EP. And the idea is that, as you probably know, MOAs, or a mixture of experts, usually activates few experts for efficiency. But if you are doing MOA deployment in a small scale, you end up actually kind of compact or putting a lot of experts into fewer GPUs. And you can probably see from this diagram, intuitively, there is going to be a memory bottleneck. And so by distributing the experts, or fewer experts onto many GPUs, it can resolve this memory bottleneck. And so you'll be able to kind of resolve the pressure for loading weights for experts, or you can enable higher concurrency, or you can also feed the right batch size for compute efficiency. And so applying this technique with disaggregated serving is going to unlock really incredible performance, as you can see from this plot. And we spent a lot of time doing the performance optimization for you. This was a partnership with Semi-Analysis, and the link is pretty small, but the link is at the bottom. So if you want to check out the recipes that we published for applying disaggregated serving with YDP, the recipes are readily available at GitHub page for Inference Max. And so I would highly recommend going there to check out DeepSeek recipe if you're interested in deploying R1 model. So far I talked about the hero use case, but now I wanted to kind of talk about the foundation, so scheduling, memory management, and then also data transfer, how that actually brings incredible performance boost with Dynamo. So let's first talk about scheduling. One of the key features of scheduling is our KB-aware routing. And this algorithm is simple, yet really powerful. And so what we try to do is we try to combine the KB cache hit rate and then also KB cache load that exists in a worker, and then try to apply smart routing to route the request to the best worker that is going to give you the best performance. So in this case, say, for example, if you are only doing capacity-based load balancing, then the router is going to always send the request to the first worker that you see at the top. But say, for example, if you already had relevant KB cache that you can reuse in the bottom worker, although it has the most KB cache load, it's more beneficial to actually load or route that request to the bottom worker, because you can actually decode much faster because you already have the KB cache that you can reuse. And so that's how the router works, just combining the two information. And the KB cache hit rate is calculated by looking at the KB events and then trying to create a radix tree. So that's how the router works. But this is a simple setup, but it actually gives you a really powerful result. And so we recently had our customer publish a blog using the KBR router, and they were able to unlock incredible performance for Qwen3 480B coder model. And so they told us that they didn't have to tweak a lot of things, but just using KB router, they were able to unlock 2 times faster TTFT, and then also 1.6 times more TPS. We're also spending a lot of effort to expand the KBR routing, and so I was not able to actually get the result today, but we verified that KBR routing with desire serving is also functional. And then we're also extending the KB router so that we can support multiple memory hierarchy, which I will show you in the next slide. So the second area is the KB cache management. And so we do this using our component called KB block manager. And the idea is that we have a nomenclature within NVIDIA, and we call the memory hierarchy with G1, G2, and G3, and G4. But basically, we are denoting the GPU memory, HBM, and then the host memory, local SSD, and then the network storage. And we want the developers to be able to use all the storage and memory hierarchy that's possible in the data center. So this will give you a benefit because as you extend the storage, you will increase your chance of getting KB cache reuse. So for example, we recently talked to a customer who only utilized the HBM memory for doing KB cache reuse. They were only getting about, say, 30% KB cache rate. But as they increase that to, say, HBM with the host memory, they're able to increase the reuse or KB cache hit rate up to 70%. And so as you increase the storage, the chance that you are going to have a KB cache reuse is going to increase. But not only that, if you have a larger storage, then you can process a much larger context. And that's why this is fundamentally useful. And because you store these KB cache, you can decode right away without recomputing the KB cache. And so this will impact your time to first token in a much more positive way. And there are these endless use cases that you can apply this to. So multi-turn conversations or code generations, definitely you can intuitively think that this is really useful. But because now you're using hierarchy of the storage and the memory, for agentic calls where you can figure out how to, or you can usually figure out when to offload the KB cache and then prefetch the KB cache when the agentic calls get processed. You can store the KB cache onto colder storage and then prefetch it when it's needed. And so there's so many different use cases that you can use KB block manager for. One result that I wanted to share with you is that, like I said, we're really trying to work on the composability of all different techniques. And so we were recently able to look at, or we were recently able to enable disaggregating serving with KB offloading. And so in this result, we're using Qwen3 32B. But by enabling G2 KB cache offloading, we were able to see that time to first token was being processed to almost more than 2 times faster. But this unlocks not just the performance benefit, but you can also have a TCO benefit, because what this means is that if you can maintain your SLA in terms of your TTFT and also TPOT, then because using the KB Cache manager is going to give you faster TTFT, you could potentially use less prefill worker in this case. And so because you're using less GPU, then you can get more TCO benefit. And so we think that composing all these things like disaggregated serving, KBR routing, and also KB block manager is going to give you an incredible performance boost. And that's what we are trying to demonstrate towards the end of this year. One last thing that I wanted to talk about in terms of system level optimization is NIXL. And so like I mentioned in the keynote this morning, it was covered. But I wanted to kind of highlight 2 distinctive things about NIXL compared to other communication collective library. So NIXL not only transfer the KB cache between the GPUs, but as you've seen with the KB block manager, we use it for transferring the KB cache across the different memory hierarchy. And so it provides a unified API for doing peer-to-peer transfer. And it's the same API for doing passing the KB cache between the GPUs or multiple hierarchy of the memory. So that's something that's quite different from other networking libraries. But another thing that I want to mention is that it doesn't have a fixed world size. And so for inference, this really matters because you want the ability to add or remove the workers on the fly. I will talk about the fault tolerance features that Dynamo supports, but something that we are collaborating with the vLLM team is supporting fault tolerance for MOE. And so in that case, say, for example, if you deployed DeepSeek R1 onto hundreds of GPUs using YDP technique, if one of the experts fail, then the entire deployment that you had for 100 GPU is going to fail all at the same time. But if you have something like NIXL, you can just effectively remove that worker and then just either also apply something called elastic AP to add another expert or remove experts, depending on how you see fit. So this gives you a more dynamic control over your inference workloads. And that's why we created NIXL. Last thing that I will show you is NIXL performance. And so kindly, Professor Zhu from UC Davis, who I think was also a PhD student at Skylab, recently benchmarked across all the different data transfer engines. And then he verified that NIXL is achieving the SOTA performance compared to other inference engines or data transfer engines. So that wraps up the part about system level optimization. What I want to highlight is that, like I said, we are in the business of augmenting the system level optimization with the low-level optimization that the inference engine provides. And so that's how you can actually unlock even more performance with Dynamo. And like I said, production-grade serving is something that we are really focusing on. And this is, if you're kind of thinking about applying these different techniques that we talked about before, yes, you can do this, but you need to be able to do this for production-grade serving. And we largely provide these 4 key features for you to go from configuration to production. And so the top 2 features that you're seeing here has to do with performance. First one is figuring out what is the best configuration that you can use to either deploy with disaggregated serving or aggregated serving even. And then after you've determined the best configuration offline, we also have an automatic way of tuning the performance based on the real-time traffic. And so those are the 2 production-grade serving features that we provide for performance. And then the bottom 2 have to do with scaling and reliability. And so we provide a way to dynamically scale Kubernetes with topology awareness. And then we also give a little bit more fine-grained fault tolerance that's more suitable for LLM use cases. So these are the 4 things that I want to talk about. But the first one is something we call AI configurator. So we talk to customers that want to deploy disaggregated serving or have done disaggregated serving and they deploy it in their production. The biggest challenge is figuring out what is the best configuration. So if I go back and if you remember the slide that I showed you about doing the disaggregating serving for Llama 70B, you saw a whole bunch of dots. We actually had to generate those dots by sweeping all the configurations, and it took us 2 days to complete this. Number one, it takes human time, and number two, you're also spending a lot of time on expensive GPU. And so we thought that maybe we can provide a tooling for doing this, and maybe it can be run on your laptop with less than a minute. And so this tool is something that we already open sourced a few months ago. And what it does is, if you call its CLI, you can specify the model that you want to run. In this case, we're showing Qwen332B, but we do support about more than 30 popular models. And so you can choose DeepSeek R1 or anything that you want to deploy. And then you can specify your number of GPUs and the SKU. And the optional parameter that you can input is also about your input sequence length and output sequence length, and your time to first token, and then TPOT. And so based on that, it will run for 1 minute, and then it will give you this nice-looking graph on the right. And it's basically comparing the performance between the aggregated serving and disaggregated serving. And I'm not so sure if you can see the X mark here, but that X mark is indicating where you can get the best performance benefit using disaggregated serving. Not only that, I had to cut this part off, but in the transcript, you'll be able to see the top 5 configurations for deploying with disaggregated serving. So that means you'll be able to see what is the number of prefill and decode that's required for you, and then also the parallelism that you need to apply for each prefill and decode. So this is an incredible thing that a lot of the developers really found a lot of benefit. We even had a customer manually tweaking this to deploy onto, say, something like L20 for Qwen332B. Right now, it supports hoppers, so H20, H100, and H200, and we're trying to add support for Blackwell currently. Also, something that we are doing on top of this is to, so at this point, we are supporting TensorRT-LLM, but we are also extending the support for SGLang and then vLLM. And the SGLang support is a contribution from Mooncake, which is a partner that we closely work together with. Oh, and one last thing. Another thing is that this particular tool will give you a YAML file to just deploy straight to Dynamo. And so we try to make it seamless, but like I said, this is also modular, and so you don't have to use Dynamo to be able to use this tool. You can just run this tool standalone. So once you figure out how to deploy with the best configuration, when you deploy, you are likely to have a traffic that looks like this at the top left corner. And so we know that for LLM, the traffic pattern can change very rapidly. And so we created another tool called Planner to help with this case. And so if you set your SLA in terms of time to first token and then time per output token, then Dynamo Planner is going to automatically scale prefill and decode up and down in order to circumvent for the spikes that happens in the traffic request. So the way that it works is it tries to predict the load, and then it tries to predict the time to first token and then also TPOT, and then compares it with the observed TTFT and TPOT. And with that ratio, it's going to look at how you can scale the prefill and decode intelligently. And we recently had our partner publish a result by feeding live traffic. Partner in this case is Alibaba ACK. You can think of them as EKS of China. And what they were able to observe was incredible. So they were able to see with Planner about 80% less SLA breach, while only using 5% less GPUs that they allocated. So this is a very strong feature. If you're deploying things, if you're deploying disaggregated serving in production, we think that you can actually take advantage of this Planner feature. But even with that, we have a really big problem because if you're using leader worker set from Kubernetes, the dynamic scaling of prefill and decode that you saw before, you can't really do it because the prefill and decode has to be scaled with a fixed ratio if you're using leader worker set. So if you define your prefill and decode to be, say, 5 prefill and then 3 decode, you can't really change it dynamically once you set it up. It also has a problem of not being able to take topological hints. And so, like I talked about, you can probably intuitively think that prefill and decode, or the experts that you want to allocate, it's beneficial for you to allocate them in close proximity. And so we decided to create something called Grove, which can help you with gang scheduling. And in this case, we can do hierarchical gang scheduling. And so as you can see on the right, we can define the group for scaling prefill and then also decode. And they can be dynamically scaled. But also at the same time, the pod click set, which contains all the pod clicks that you see in the green boxes, can be scaled all at the same time. And it is also capable of taking the topological hints. So we think that this is a great addition to helping you to do production-grade serving. We showed this to a lot of the customers who are deploying disaggregated serving in production, but they had to do manual scaling of prefill and decode, and they really loved it. But even then, there's even more problem because for LLMs, Kubernetes kind of provides like some standard fault tolerance, but for LLMs, you need much more finer grain fault tolerance. And so here are some of the features that we support within Dynamo. Say, for example, for router and the front end, we try to make it so that the router state is shared across. And so if one router goes down, because the router state is shared across, that does not have a lot of impact in terms of the system. Something else that we support is request cancellation. So say, for example, if a user is trying to do a tool calling, and you have to provide a structured output, if the user cancels that request, and if the request goes ahead and then compiles the structured output, that is a really big waste, because if you were to process that at scale, you are going to actually have a heavy penalty on the compute. And so we have a support for request cancellation that permeates throughout all the components that is involved in inference serving. And then you can easily cancel the request. The third one is being able to do migration of the request. So if one of the workers go down, then we try to make it so that the request can be just automatically migrated to a healthier worker. There are other things that we're working on, things like request rejection, to avoid overload of the system. But we think that these 4 major features that I just talked about, going from offline configuration to online performance optimization, then to being able to dynamically scale with Grove, and more finer grained fault tolerance, that's going to really help you when you deploy LLM serving in production. So that kind of wraps up my talk. With Ray, these are some of the things that we want to work on. So just like we supported RayServe with Triton, we want to be able to integrate with RayServe for Dynamo. And then we know that a lot of the RL libraries can be used with Ray. And so we want to enable all these libraries by supporting dynamic load balancing for the rollouts. So those are kind of the 2 directions that we want to explore with the Ray team. So thank you so much. That concludes my talk. If you are interested in this project, please check out our GitHub repo and give us a start. Thanks a lot. Do you have time for questions, or? OK. I think there's a microphone at the center, so if you want to ask questions, please use it. Thanks a lot.
Hi, thanks for the amazing talk. So is there a way to use these components with RayServe today? Like if I want to take 1 or 2 components and...
I think we probably need to design it. I did talk to the tech lead from Anyscale who works on RayServe, and so we'll try to have some more conversation as to how this could be facilitated. So yeah, not yet, but we'll work towards making it happen.
And I mean, the components are very, very interesting. The KV router, like, have people used it like separate from Dynamo as like an AI router?
We actually provide an example on our GitHub repo. It's called standalone router. If you only want to be able to use the router, you can actually do that. The only thing that it requires is vLLM, and then we have Python scripts where you can actually do the KBO routing, so you can see it for yourself. We had a request from a customer that they only wanted to use the router, and so that's why we decided to create that example.
Great, thank you.
Yep, thanks.
Howdy. Yeah, that was great. I was wondering, for metrics and observability, do you have any like Prometheus exporters or some sort of metric gathering?
Yes, we do. We have a whole page on our documentation talks about all the metrics and observability features that we support. And so I'm not going to give you all the metrics and observability, but we spent a lot of effort trying to make that happen, because for fault tolerance, you absolutely need to observe to make those decisions right. So.
Cool. And I was also wondering, I imagine you have a lot of like runtime optimizations. I was wondering if you had any like compile time, or is there a space for that, or is it just like runtime?
Yeah, for those, generally we try to leverage inference engines. Like I said, we're in the business of thinking about it as an ecosystem, and so we want to work with the partners. So maybe a bit of history. Before disaggregating serving was supported, we patched the vLLM to make disaggregating serving happen. And then there are some other optimizations that we put in. But we decided to upstream all the optimizations that we made to vLLM as an example.
Amazing. Thank you.
Yep.
Thank you. The AI configurator running from a laptop while estimating H200 performance. How does it do that from a laptop? Like what parameters, what assumptions are there?
Yeah, so we try to use, we look at the kernel execution time for TensorRT-LLM, and when we support other inference engines like SGLang or vLLM, we'll do the same. But basically, you look at the kernel execution time, use that to actually predict the performance projections.
So like those are tabular data that has been generated already, and the run that's like just interpolates them.
Yes, that's correct. So the data itself is also open sourced. So you can either take that data and make use of it, or we also provide a way to add your own model so that, well, two things. You can add your own custom model. There's a guide for it. And then you can also bring in your own metric for measuring. So like I said, there was a customer who tried to run Qwen32B on L20, and that they kind of added their own metric to figure that out with the AI configurator.
Okay. So about the router, about composability, modularity, the router, it looks like an application level router, right? Do you have a component that can be, for example, plugged into Envoy to go to the mesh layer? Like,
yeah, we do have a support for inference gateway, and so yeah.
Okay.
Okay, thanks.